Okay. So, yeah, thank you very much for the invitation. Um, my name is Daniel, and I'm currently a postdoc at Ghent University. Just for those who might not know me, I've been working on causality during my PhD, and oh, sorry, can, yeah, okay. I've been working on causality during my PhD, and I still continue to do that. And I'm currently doing this here at Ghent University, trying to use causal inference methods to understand drivers for extreme heat. Um, and there are a couple of things that I've been playing around recently with this, and I wanted to share some of these with you. I would also appreciate your feedback because this is also something new that I'm exploring, and it's something that I'm hoping to improve myself as well. Um, so just to list a couple of contributors to um, the line of thoughts for this, which includes some of our colleagues here, including Alison and Ben. But yeah, I want to appreciate my co-authors in the first row, uh, Diego, Thomas, and Cass, for their thoughts on everything concerning this particular work. Okay, so here I start with the Book of Why, which is by Judea Pearl and Dana McKenzie, and I really like this book because it gives us some helpful fundamental things that I think are relevant for moving from causality to machine learning. And actually, this work was sort of inspired by a YouTube video that I watched of Judeo Pearl when he was given a couple of thoughts on this particular book. And so you'd find me referring a lot to this particular book. Um, One of the things that he mentioned, which is the hierarchy that he provided, the ladder of causality or causation, the hierarchy of causation, is something that has sort of that got me thinking quite a lot. And so that there are three levels that he speaks of, and the first one is associations. This is where correlations come in. So basically correlations, if you have the base of the hierarchy. And then you move from there to some sort of intervention, which we would call causality. Um, and then you go to counterfactuals, which have become very, very popular. I think it was mainly after this book, probably, or the papers that he wrote concerning the ideas in this book, that we had this outburst of publications on counterfactuals and applications of that in machine learning. But I found this to be very intriguing, especially the fact that most machine learning models are operating at the level of association. So they are mostly working at the level of correlations. And of course, we could also correlations in regression models. And so this is really where they're working. And I remember that in one of the talks that he gave, he said something like, if we want our machine, this was actually even before OpenAI made their reasoning model known, or even before DeepSeek also published their reasoning model. He used the word reasoning, that if we want our machine learning models to reason, we would have to go from association to causality, and then also come to interfactuals to really validate the causal knowledge, or um, the causal graphs that we are building with that. And I realized that a lot of papers also got published on these ideas, although I do say that most of them were still at the level of explanatory AI and not really interpretable AI, which is where Judeo was advising that we move to. Now, somehow, when I was listening to this talk, this paper by Ben and Drewy and I think it's also gray. The three of them. Uh, it came to mind, and it has sort of haunted me for a long time now. I think that anytime I've spoken at this forum, I've always referred to this particular paper, and I really like this paper a lot because it's really driven quite a lot of things for me along these lines of thoughts. So in this paper, Radley et al. Suggests that we move beyond predictive performance assessment to functional performance, where predictive performance is sort of you are more interested in the accuracy of your model, of your climate model. So if you design a climate model or a simple eco-hydrological model, you are interested in getting values that are close to, say, observations. So for instance, if you have outputs of sensible heat and latent heat, or maybe evaporation, soil moisture, whatever it is, you compare that with your observations and you try to see if these are almost the same. I'm sorry, I don't, I'm not sure of how many of us are familiar with these papers, and so forgive me if I'm repeating things that you already know, just to make sure that no one is lost in this talk. And so along these lines, they come up with a functional performance where they are using here, I think, mutual information. The approach that was developed by Ben and Praveen somewhere in 2010, which Alison also built on. And they provide a very neat way of not just assessing the accuracy, but also the sort of a link-based assessment. So getting the right answers for the right reasons. So why are we getting this level of accuracy? Why isn't it so good here? Because sometimes we can have good accuracy, but we sacrifice the processes that are connecting these state variables or these fluxes that we are working on. And so I really liked this because for me it gave me a way of looking at machine learning from this perspective, which is that most of also when we look at machine learning and we evaluate our models using RMSE or whatever it is that we do, we're also trying to get as accurate values as possible. But this could be also at the expense of interpretability. Why are we actually getting these values? And so I was thinking of how to incorporate these ideas into what Judea Perel was also talking about. And I think that in the paper that I shared as the reference, in that paper they provide a graph. I don't have it here in my PPT. Somehow I thought I did, but they have a graph that they compare the accuracy of the machine learning model to the interpretability. And I like that figure so much because they provide a nice trade-off. So definitely, if you are trying to improve interpretability, that wouldn't always guarantee that you have a high accuracy. And so in the graph that they show in their paper, if you go back to that paper, you would see that they show how their approach sort of compromises, trades off, and it's the same idea with this paper by Ben and the others, that they also sort of show that there has to be some kind of trade-off that provides a structural performance which combines the predictive performance and the functional performance. And so I really liked this a lot, and since I read the paper, I was really thinking about how to utilize these ideas, not just in data assimilation or running of our climate models, but also in machine learning. And I'll speak about that later. Sorry. Okay. So the way that I decided to approach this was to use the Liang-Kleeman information flow. And I'm not sure, again, about how many of us are familiar with it. So here I just give a quick crash course on this. And for those of you who are interested in it, I highly recommend Liang's 2016 paper published in PRL, which has probably about almost 200 equations, because he sort of wrote. I remember when he was writing that paper, Liang was my co-supervisor during my PhD, and I remember that he said that he had been sort of dared to write that paper. So he wrote a long paper with all these derivations because some people were thinking that his approach was a bit speculative, and that he was sort of jumping steps. So he really wanted to emphasize on every single step. So if you want a very nice tutorial on that, I highly recommend it. One of the things I like about the Liang Kliman information flow, not that he supervised me, but I actually, there's a reason why I chose to use it, and back in 2014. And one of the reasons was that in the first time I heard him speak about this, he started by saying that causality is a real physical notion. And I thought that that was very, very interesting, especially when he said that in the Newtonian sense, because ever since I learned about Newton's laws of motion, this has really been some of my best. It's been one of the most exciting things in science, but how he connects that with causality, I found that to be very interesting. But the point that he's making here is that causality should not necessarily be a statistical relationship or purely statistical relationship, but that it has, the bedrock of it, or the foundation of causality, has to be a physical notion. And it's something that has to be derived from first principles, which is something that most causal frameworks do not do. And so he's done quite a lot of work on this with quite a lot of papers that he's published, most of them in entropy and PRL, so you can also check them out. But he showed that under a stationary assumption here, that when you're given a deterministic or stochastic system, that the rate of information flow from one time series x2 to another time series x1 can be formulated as we see over here. The rho that you see over there is the marginal density of x1, and whatever subscript that is written down there. F over there is the diffusive term, and then we have E being the expectation, mathematical expectation. Now, the basis for this framework is that if you are considering the marginal entropy of a variable x1, if you want to see how another variable x2 impacts it, you can freeze x2 and see how much of x1 is lost out of it. And so when you do that, you get the term t2 to 1. And so this, it's not entirely a Pearlian causality of intervention, but it has the idea of intervention here. But one of the reasons why I like this is because we start with a dynamical system, and we extrapolate the information, the entropy. We estimate the entropy from that, and then from there we sort of express that using some statistical relationship. And here he uses the maximum likelihood estimation to obtain a sample covariances formula. So here we have a causality formula. We have a formula that is actually attempting to extrapolate causal properties. That is not the intention. That is not the original intention of this information flow. The original intention is to compute the information flow, but information flow does bear properties of causation. And so under the right assumptions, we can extrapolate this causal information from it. And so he did that for a bivariate form, which you see over here, and then also for a multivariate form that you see over here. I include this equation here that he provides because it's one of the interesting equations that brings us to correlation. Correlation is not causation, but causation is correlation. And of course, that makes sense because if you go back to Judeo-Pearl's hierarchy, at the bottom of it, we have correlation. So if there is causality, there has to be some correlation. Some correlation. It doesn't necessarily mean that correlation has to be that high, but there should be some correlation over there. But here, what he does is that he rewrites this equation in terms of correlation. So he takes his information flow equation that he obtained, and then he rewrites it in terms of correlation. And what he shows here is that if R is 0, then of course this will be 0. So if R here is 0, then this will be 0. But if this is 0, R doesn't have to be 0. So which means that if there's no causality, it doesn't mean that there is no correlation. And this is where we can sort of get spurious correlations, which is that sometimes there is really no causality. Causality might be significantly, now or insignificant, but then we would have some correlations there. And so causal inference methods that are sort of dependent on correlations may, in these sort of situations, collapse or provide spurious causalities. And so I found that that was a very nice thing. And that, in a sense, is a mathematical way of saying that correlation is not causation, but causation would imply correlation. All right. Please feel free to also stop me at any point if you have a question. And since then, since the development of this approach, there's been several applications, which includes our geosciences. I was happy to do the first application of land-atmosphere interactions, applying it to soil moisture in the atmosphere. This has been also applied to air-sea interactions, CO2 temperature. I also used it in the first application of data assimilation, evaluation of data assimilation. That was under an ESA project. And then it's also been applied in quantum physics as well, neuroscience, medicine, economics, machine learning, as I'm going to present here, and also in previous publications as well, data reconstruction, and then also another thing that I'm working on with this Liang-Kleeman information flow is that I'm taking physical equations that we use to measure or to estimate couplings between the land and the atmosphere in my case, and I'm rewriting this equation using this information flow, and that has been quite fun. Doing it, of course, it's not also easy to do as well because it's not a one-to-one relation, which I will speak on later. This was also featured in Physics Today with the title Quantitative Causality, so you can also check it out as well. All right, so this is where I come in. So somewhere in my PhD, one of the things that I realized was that the Liang-Kleeman had, the assumption of stationarity, because if you look at the Liouville equation, it's assuming some sort of stationarity. The trajectories, we're not really tracking the the particle in time, sort of in real time, but actually we sort of do some kind of averaging where we get the relationship, and this is not very helpful when we really want to understand causality. And the reason is that causality will change over time. This was also what Alison explored in her thesis as well, which is that causality does change over time, and not just that, also over space. So I'll give more information on that later. That given the same variables, how or why does causality change over space, across space and time? So one of the things that we decided to do was to develop some kind of time varying framework of it. Now, of course, the ideal way, or a very simple way, would be to use a moving average and then just estimate it. Something like what Ben did in his, I think it was 2011 Land Ecology, if I'm not wrong, about the journal. He did that in his paper for his approach, which was a very neat one. But one of the things that I quickly came to when I was applying just a normal moving window was that selection of that window length was very, very complicated. Um, how how much, how many, how long do you make your window length? If you make it too long, which is very good for a sort of a statistical computation, um, then you sort of smoothing out information. And if you make it too short, then your computation is also not extremely reliable. And so one of the ways that we decided to approach this, inspired by a paper published in 2010 by Havlik, I think, Havlik et al., they applied it, they were applying a granular causality to a neuroscience problem, and they did very well by providing some kind of dynamic granular causality over time using Kalman filter, and we thought that that was a neat application. So I decided to also apply Kalman filter to this. So the Kalman filter is used to estimate the covariances at each time step, and that gives us some kind of time varying framework. I applied it to theoretical models. So I built a coupling system, and then I estimated the time varying information flow using this approach, and also applied it to soil moisture. And later on, I supervised a PhD student to extend this to the multivariate framework. So I started with the bivariate framework, and this was also extended to the multivariate framework. So this was a very neat thing that we were able to do. But one of the things that we hadn't done was to explore. It was to explore under which conditions the bivariate form and the multivariate form diverge. So this is a paper that was just submitted. Um, it's currently under review in Earth Systems Dynamics. Those of you who would want to comment, please feel free to read it and comment. But in this paper, actually, this paper was it didn't start as this way. We just started by applying the time varying causality to a couple of variables that we had. We're trying to understand how drought impacts the ecosystem, or impacts biomes, vegetation. Um, and the question that we were asking, because what we kept doing was that we started with two variables, with soil moisture and a vegetation proxy. Here we're using LAI, and then we asked ourselves, well, should we use GPP? So we tried LAI and GPP, but then we also started asking ourselves another question: is soil moisture LAI enough? Is it sufficient, or should we add other variables? Confounding variables. So we added VPD, and then we asked the question, what else can we add? And then we kept adding and adding, and at a point in time, it just got ridiculous. And we were asking ourselves, why is it that sometimes the bivariate will diverge, the multivariate will diverge from the bivariate structure, and sometimes they would also look almost alike. And so we actually stopped the work that we were doing, and we decided to answer this question in this particular study. And while we were doing this, I sort of got an idea that, wow, this would be nice to apply to machine learning, and I'll talk about that very shortly. But this was sort of what was happening at this point. So in this particular figure, what I just want to emphasize here is that here we provide the difference, which is the delta information flow between the multivariate and the bivariate form. So here, multivariate form, I'm using the form that that would sort of apply that would include all the variables that you see here. So here we're talking about either GPP or LAI being the target variable, and then the predictors would be soil moisture, VPD, temperature, and and radiation, I think. Yeah. Yes, Hoshin.
Just a quick question. You started on it, but could you clarify the y-axis,
Uh,
the
oh yeah.
units,
Oh sorry.
and
Yeah. Yeah.
And could you help me understand uh, what a particular value means? How, what's large,
All
what's
right. Okay.
negligible, what's
Yeah. Yeah. Sorry about
in other
that.
words,
Yeah.
can you bound this in some
Yeah.
sense? Yeah.
Yeah. Yeah. So I'll probably just go to this one. So here, Liang used here he used the natural log, and so we obtain something that is measured in knots per unit time. So that becomes the unit of the information flow that we have over here. Um, and the, and the way he expresses it is by saying that a positive value would mean that x2 is a source of uncertainty for x1. So x2 makes x1 more uncertain. And if it's negative, then x2 makes x1 uh, more stable or stabilizes. It provides equilibrium for it, which is always a very sort of a very technical way of expressing it. And the way I like to say it is that a positive value means that x2 amplifies the variability of x1, and then a negative value would mean that it would dampen the variability of x1. So here we are not talking in terms of x1 x2 increases, x1 increases, and x2 decreases, x1 decreases. Yeah, definitely not like that at all. And I'm saying this because I've had this continued discussion with reviewers every time I submit I submit a paper, and this almost every reviewer tends to look at it as some kind of correlation or regression interpretation, but that's not what we have here. So if it's very very so the stronger the value in essence, the more information flow, and of course we could assume that that means a higher causality for it. But of course, Liang also showed that it is important sometimes to normalize the information flow. So when you normalize the information flow, then of course we sort of we are not bound by a particular reference for this. And so in 2015, he wrote a paper that he suggested normalizing it by looking at the whole entropy budget. And so I didn't show that here, but in that particular
So,
one, what he does is that actually yes, you can if you look at just this T21 DH1 and DH1 and then DH1 star, where DH1 is the marginal entropy, and then DH1 star is kind of like the I would say the background noise. And so he sort of normalizes it to obtain some kind of a normalizer called Z, and then he uses that to express that in a normalized form. But yeah, that is kind of a quick.
effectively, it's not bounded. It can go from minus infinity to plus infinity.
Yes, 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 yes. For the absolute form, it's not bounded.
So how do you know if a value is significant?
Yeah.
That's, I guess, my
So
question. Yeah.
that's a good question. Yeah. So to do that, we do statistical testing. Um, we can use you can use something like so what we use is we use the oh my, it's like everything has suddenly disappeared. We use the we use um, the inverted covariance, which is the Fisher information matrix. We use the Fisher information matrix here in our particular case, but you can also use bootstrapping as well, which should work. So in our case, we have consistently used the Fisher information matrix, and that one of the reasons for using that is because it's easy to do that if you are working with covariances, and so you just apply
Sure.
that, yeah, to estimate it, and if it's significant. So for instance, in this one over here, yeah, in this one over here, uh, the the red lines that you see over here, these are my Fisher information matrix values. And so whenever the blue one is greater than the red one, then we call that significant. But then, of course, in a normalized version, then we have everything going between -1 and 1, and that simplifies it. And in that case, we can compare magnitudes of different systems.
I guess another way to think about it would be it's significant if it exceeds random chance
Yeah,
by
yeah,
some
definitely.
factor. I'm not
Yeah,
sure exactly how you would measure that, but is that something you've thought about?
yeah. In Of course, in the normalized framework, this is definitely a way that we think about it. I mean, we are essentially assuming a Gaussian process, so we would definitely want that as well. But yeah, so far that is how we have thought about it along these lines. Yeah,
Okay, thank you. Sorry.
you're welcome. So I'll go ahead. Yeah. So the idea here for this particular study was just to understand why these vary. Now, while we were learning it, I realized that we could somehow generate a bunch of statistics that would describe these deviations. And what I'm going to say here might sound very crude, and so I'm trying to be careful. The idea here was that if we keep adding variables to the network, we might get to a point where there is a saturation. So an example would be for this first subplot that you see over here, which was actually one of the most interesting plots that I saw. That regardless of how much you include, how many variables that you include, it didn't really change the causal structure over time. However, for the same variables, do I show that here? Yeah, for the same variable. So this is one location, and for the same variable over in another location, you could also see that this was almost a similar story. Sorry, although the delta information flow was just a little was just a little more than here. And when you change the variable, when you change the main predictor variable, you would see that there are differences that we are getting over there. And this puzzled me. Of course, it's nothing strange, but it puzzled me. The question that got me asking was, under which conditions do we have these differences here and there? And so we decided to explore this. And one of the things that we quickly understood was that we were somehow developing some kind of state-based information flow, and that under extremes, under here I'm talking about climate extremes, the causal structure behaved in one way than compared to, say, a normal situation. And that is actually very helpful because it sort of gave me another idea that we could perhaps do something that would look like a Rayleigh entropy, as presented by Milan Palus in his recent Science Advances paper, where we could sort of see how Shannon entropy might provide some kind of information here. So here Liang uses the Shannon entropy. Everything here is based on Shannon entropy. But then we could also sort of begin to look at how it behaves at extremes, which Shannon entropy is not meant to do, I think. I may be wrong there, but it's not meant to. I don't see it being meant to do that. It's of course looking at sort of the dominant behavior over there. So we applied it here. We got some nice things, and I realized that we could develop more statistics out of it. I'm sorry. Another thing that I also realized here was that that while the differences between the multivariate and the bivariate, could be large, sometimes the correlation might also still be very very large, significant. For instance, here we have a high delta information flow, a slightly larger delta information flow, but then the correlation is still very very strong here. Or in this case, for instance, delta information flow is very large, but then the correlation is also quite large. And so I decided to look at, the correlation versus the delta information flow over quantiles of soil moisture and VPD, which were the main predictors that we were using, and to see how the information flow changes. And so this is for one particular location in China, and you can see that if you look at this coupling, even with this with soil moisture to LAI and soil moisture to JPP, you get something quite different. And so here, the target variable, which is quite chaotic, more chaotic, JPP being more chaotic than LAI, we would see that we have larger delta information flow, which is the difference between the bivariates and the multivariates. But then, of course, the correlations were also quite high. But then once you changed it from soil moisture to VPD, you were getting a more nuanced story. And so the question that I started asking myself was, if we look at a machine learning model, or if we are trying to apply this in machine learning, these are things that we have to be quite mindful of, which is that that when we train our machine learning models, how do we assign weights if we are doing some kind of causally informed machine learning? Because apparently, these weights would be different if depending on the time point, which is shown here. Here's over sometimes the delta information is smaller, and over sometimes the delta information can be quite large. And for the same variable in different spaces, you can also see that it behaves quite differently. Of course, this could be also impacted by the averaging of the pixels that you are using, which is a study that is currently being done by Rebecca Herman for PCMCI, I think. But then, of course, we could also learn quite a lot of this, and this could already begin to help us proceed with caution when we are doing some kind of causally informed machine learning, which is that we train our machine learning to sort of with some sort of a causal framework in the attention, but then the causal structure itself is highly variant, or could be highly variant over time. And of course, we understand the difficulties with transferability. So having created a model for one particular location, it is difficult to extrapolate to another location. But I was thinking to myself that, well, if we can introduce causal information, then hopefully, even if we change the location, we can still do well, assuming that we respect that causal information will change both over time and space. So I decided to play around with this idea. This work was done quite in a rush, so there are still quite a number of limitations that I will also point out here. So the first thing I did was to create some sort of statistics out of the work that I just showed you, out of these studies that I just showed you, and we were thinking about expressing this in some ways in terms of the mediator, or what we call the confounder. Now this one over here is where I was saying that we have a sort of a crude thing here. Here we are calling something causal sufficiency rate, which of course I understand that we almost can't say that because we haven't included almost every possible variable. But here the causal sufficiency rate is just merely the closeness or the deviation between the bivariate form and the multivariate form. So if they are very close, if the bivariate form and the multivariate form are close, then we assume that there is a level of causal sufficiency that has been attained. So for instance, we could argue that this is almost quite believable to be causally sufficient. And because I don't show the others, but it didn't matter how many variables we included. And it could be a problem of the Young-Kleeman information flow itself, which we will have to investigate. But under all the assumptions that formalism comes with, we could make some kind of you know inference here that it may have reached causal saturation, so that regardless of how many variables you include, it didn't change. Now, I tested this with my own generated variables. I don't show that here, but I can show you if you are interested in the paper, or you can also see it in the paper in the appendix, where we created a toy model and then we tested this idea over there, and it was quite helpful. But we realized that we could sort of also include this statistics where we are saying that if the bivariate form and the multivariate form are not significantly different, then we may have reached some kind of causal sufficiency. Now that's definitely good news in some cases. And so from these, we came up with these four indices, and then we sort of normalized them to develop another index called the causal importance score. And so this causal importance score becomes our basis for applying the weights from causality, in this case the Young-Kleeman information flow, to any kind of a machine learning model that we might be interested in. So this is an example of these indices that I applied to these variables and obtained these graphs. So here in this case, I applied it to two different locations, and I showed that we can describe the causal characteristics based on these indices, and use that to generate the CIS. I have not included some information here. I'm not sure if one of our reviewers is here as well, but here we come up with the CIS equation. Okay, so we come up with this equation where we have these weights over here. Ideally, of course, if they are all important, then we could sort of make them all one. But here we can sort of, based on the analysis that we develop here, we can develop the CIS score and then use that in our weights form. For a random forest, I think this is pretty straightforward to do, but with a neural network, we thought of including some kind of regularizer, and this is how we sort of came up with it. So that we would get this equation, which is equation 12 over here, with our regularizer being lambda over here, and I tested the idea of lambda across multiple values to see how that impacts our results. Of course, lambda being 0 would mean to sort of remove any causal constraint. So here we force our neural network, to sort of behave or to bear the properties of our causal structure that we obtain from the information flow. And then, of course, I did that over multiple epochs, and then evaluated it. I'm sort of simplifying that here. And you can ask me more questions. If you also want to see the equations, I'm happy to share the paper with you privately. So with our loss function, I realized that there is a high dependency on lambda, and I tested it, hoping that, of course, we will get some kind of saturation here at this point. And then we can look at the RMSEs of that. And here, when I say RMSEs, it means that we are comparing with the information flow itself, and to see how different the neural network is from the information flow. And then of course we can get some sort of convergence alpha, which is I haven't shown here as well, unfortunately. Oh yeah, okay, yeah, over here. Um, that we include over here in the equations. So we tested all these variables and to see how they all give us helpful results for the neural network. So what we did was that we applied this to a random forest, which is we didn't do anything to the random forest. It's just a normal. We just built the random forest without applying any sort of causal information to it. And then we also applied it to a neural network where lambda is 0, so that we remove all sort of causal constraints from it. And then based on the analysis that we had done, we chose a lambda value and then we applied it. And the results demonstrated that, so this was a very simple implementation that I did, like a very, very simple, simplified implementation. That if we use a CIS score and we apply that, can we get our neural network to look like our causal framework? And the results show that it is possible. So here, if you look at the first row over here, this first column is a comparison with a baseline random forest, and then also in a sense the baseline neural network, and then the neural network where we include the lambda parameter. For the sake of the brevity, the requirements that were given for the paper, I couldn't test quite a lot of variables, which is what I hope to do in a proper research, a proper study after this, where we have to really stress test quite a lot of the parameters that we are using here. But here I only focused on lambda because it appeared to me that it made the biggest difference. If you look at also the RMSC over there, you would see that it made a difference. And so since it made the biggest difference, I wanted to rather focus on that. And so you would see that compared to the baseline random forest, we see some differences with the CIS. So here, and then here we also see that if we remove causal constraints, then we also get significant differences. But once we begin to apply causal constraints to it, then we get very helpful results that are much closer to the causality. This is assuming that we trust our causal framework. I should definitely point that out. Assuming that we trust our causal framework, then we can import that knowledge into our neural network. Now, of course, if you change, so again, we realize that this, if you changed the location, it was also very, very, very helpful. So, of course, I tested only 2 locations here, so I can't say, I can't say that it holds for everything. But we can see that in terms of transferability, it makes sense. And we can sort of do much more with this. Again, for me, it was I definitely spent more time. I've spent a lot of years thinking up to the point of the CIS, but from the implementation to the machine learning, this is actually something that I actually just did just swiftly because I found that I thought it was an interesting thought experiment, and of course submitted it to a conference, which is a conference that I thought I wanted to get more feedback on that on these ideas, and of course I think that this is also a great platform to get these feedbacks from you guys as well, because I know there's a lot of experience here. But this is the idea here, and this is the last slide that I'm showing, and I'll be grateful if you can also critique and ask more questions about this, and if you need more explanations, I'm also happy to provide. Especially, I know that most of you will be paying attention to this particular figure. I was fortunate to work with a machine learning um, person from in our office, and he provided a couple of guidelines for these. But I think there is still quite a lot to test. For instance, one of the things that I don't include here. So here I'm just looking at some kind of one-way causality. So here, I one of the things I don't input in the causal framework is that I don't, or at least for the CIS, is that I don't include from the other target from the other predictors to the targets. I don't include that information. And one of the reasons why I did that, which I don't talk about in the paper though, is that I wanted to test this idea here. I wanted to test this particular idea here of this one where we have almost some kind of sufficiency here, and then for a particular case like this where we have a significant difference, or in a case like this where we also have a significant difference between the bivariate form and the multivariate form, and to see that, well, sometimes some variables might have really the information that is needed to provide causal information. And then another thing that I don't test, which is already embedded in the Liang-Kleeman information flow. I haven't shown it in the background part, is that the Liang-Kleeman flow also provides marginal estimates, and so we can also see how a particular target impacts itself, which is very important. And I don't do this as well. So there's still more room for improvement and to expand more ideas as well. We would definitely also have to think about averaging and how that impacts, because so here what we did was that, as you can clearly see, I use the time series from a location, but it's not just one pixel. These are a couple of pixels that have been averaged. And one of the lessons that we learned from this particular study was that this averaging was not always optimal. So in the location over China, it wasn't a big problem, but in the location over the Amazon, it was quite a challenge. And so averaging also really impacts how much causal information that you are smoothing here and there. But these are challenges that we will have to deal with and somehow gradually understand. The other point too is that how many variables, can the Liang-Kleeman information handle, which is very important for applying in the machine learning, because if you have a problem in machine learning, you want to import causal information, and then you have a lot of variables, which is actually a current challenge that we are dealing with in our group, which that we've already done machine learning without causal information, we had very nice accurate values, but in that particular one, the students used about, I think, more than 50 variables downloaded from ECMWF's database. Now, if we are going to start applying causality in that, do we apply it to to all the 50 variables? This is a question, and can it sustain this much variables? There is a paper that says it can, but I'm still a bit skeptical about how much that is true. But I also think that one of the things that we can do in such a case is that we could also create a hybrid of I would say supervised and unsupervised, where supervised here means that you are forcing the causal knowledge into it. And so we could, I don't know, there could be a hybrid of letting some variables be trained through the process and other variables sort of be forced, assuming that you know that some variables are very relevant, or you want to emphasize the physical importance of it. But anyway, the idea here is that because the Liang-Kleeman is based on is developed under the assumption of, or is developed with the assumption of causality being a physical notion, then what we are saying here is that we are obtaining not just a causal graph, but really a causal graph that describes a physical, a dynamic system, and it's not just statistical relationship. And somehow we can import this into the neural network or machine learning model that we are building. Now that bottleneck is a difficult thing to do, and in the paper that I shared, they really did a very smart, um, you know, uh, transfer of knowledge from causality to machine learning, which I think I have more work to do for the pipeline over there. I try to do something in my um, in what I present in the paper, but I think there's still more work to be done. I think the other team had spent quite a number of years really thinking about this problem, but especially like the question that Hoshin asked, since the information flow is it has it has values. It's an absolute value. You know, then it's better for us to use the normalized form, not the absolute form. And so it's better to use a normalized form that will allow us to do the transfer of knowledge more easily without overthinking how these quantities would impact it. Because if we use the absolute form, then we are not just importing, like normalized weights, but we are actually importing physical quantities. And so these are all questions that I'm thinking to myself, and I'm hoping to deal with at least this year and the next if there are still more questions that come up. So I'll end my talk here. I wanted to end with my own thoughts on my own critiques of my work before you come in with yours as well. And I look forward to your questions and your suggestions as well. Thank you. Joseph.
Yeah, thanks, Daniel. That was a nice talk. I'm wondering, just so I have like a clearer understanding of the information flow metric that you presented, does it have any concept of like a conditioning set or a adjustment set? So, for example, transfer entropy, it's like the previous lags of your response variable. What's the conditioning set for your metric?
So if I've understood you well, the the basis for the information flow, and I had this conversation with Liang or San quite a lot about this, especially when I started reading Ben's paper, um, talking about the lags, which we had a lot of emails back and forth. Uh, and so here we assume we have a Markov assumption, right? And the assumption here is that if there is this kind of sort of here, I guess in machine learning terms, we'll say attention, right? If there is this, if there is any lag of impact of your influence, it would always go through the most immediate time step, before the time that we are actually focusing on. And so that's the assumption that he uses. And Young is very convinced about this. We really gone back and forth on it. And an example that he gave here is that for him, and I think I have to clarify this, is that the Liang-Kleeman is looking at directed causality. So it's really direct causality. And the assumption here is that if x2 is only significantly causal to x1 at a particular lag, at a particular lag alpha, then it is essentially not directly causal to, to X1, because it goes through another variable or something like that. If it's going to be lagged, then it definitely going through a certain process. It's not going to directly impact it, and that was his objection, and so he still insists that we just use a sort of an Euler difference, and that is more than enough, instead of taking the lags. But there have been other people who have explored it. So there's a paper by Stefan van Itzem, where he explored different lags as well. And later on, Liang himself explored this when he applied it to machine learning for predicting El Nino. So he applied it to neural networks, and then they did a 10-year prediction of El Nino. And here, what he did was he used several lags over there. But when it comes to causality, he's still convinced that we have to look at the most immediate thing and assume that it is causally sufficient. All the causal information is running through it. And this is also a conversation that I had with Ben about 2 years ago. And Ben is also thinking that this has to be the case, that we have to move transfer entropy towards that direction, where we can get all that causal information in the previous time step.
Right. So that makes sense in the time axis. So how does your conditioning set change when you go from the bivariate case that you talked about to the multivariate case? So do you just add all the variables that you have to the conditioning set?
I'm sorry. So when you say how does it change, you mean how does the information flow change? Is that your?
How does the so I'm guessing somewhere in your definition of the information flow, you have some like conditional probability distribution or some conditional expectation or something. That stuff that you're conditioning on, or this like
Okay.
set of variables. I'm guessing
Yeah.
it's a set of variables that you're
Yeah.
conditioning on. How does that change um, when you have like five variables versus one variable in your
Oh, okay.
system?
Okay. Okay.
Yeah.
Yeah. So this was actually what we were investigating in the paper that I showed. Not just how does it change, or under which conditions does it change? Why would it change? So one
But
of the
I'm not
things
even
that
talking. I'm saying just the input to your algorithm, like what is changing in the input to your algorithm, not even uh, the result. I'm just saying, like, uh, yeah, yeah. How does the kind of mathematical formulation change?
okay,
Yeah,
I guess so. What we are looking at is how. So it's still a pairwise information flow that we are doing. So
mm,
it's still x2 to x1, but we do x2 to x1 by freezing the other variables that we condition on, and to
right.
see how removing their impact would change the causality.
So you're just blanket freezing
Yeah,
all the variables that you
yeah,
have. Okay.
freezing the variables. Yeah, um, yeah, yeah. That's actually what is happening there. Because at the end of the day, what we are trying to look at is there some kind of direct information flow? We are not looking at indirect information flow here. So we are trying to remove any variables that may confound the relationship between the two variables, and that's what
Right.
is going. Yeah,
Yeah, because the reason I was asking is just I was trying to see if there was a connection with Pearl's backdoor criteria.
yeah, 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 yeah. It's something that I've also sort of tried to see, but yeah, I wish that it was more Perlian, but it's It's not.
Thanks.
Yeah,
I
Alison.
think that I think that one of Joe's questions just got one of my practical questions answered about the actual like computation of the information flow type. But I just wanted to say I feel like this is a really cool and like well thought out and better version of kind of what I was worrying about last semester when I gave a presentation here, which is kind of like the idea that sometimes the information is there and sometimes it's not, and there could be a lot of reasons why at a given time, if a model lacks in predictive accuracy, like, you can trace that error back to was the information not there? Like what were the drivers not adequate to possibly predict your target, or is it something else where it's like the type of information is just more complicated and the model was unable to handle that? Anyway, I thought that was a really cool presentation and definitely really, really useful.
Thank you very much. Yeah, it was also, and really this is this is really inspired by Ben's paper. Then um, it's it's also something we thought about when we were applying to data assimilation, um, uh, to see that okay, if we have improved if we have improved the state uh, variables, have we somehow deteriorated the relationship, or if we haven't improved it, you know, is there something going on? And it was, we were very surprised by the results, which was very good news. It's good to be surprised sometimes. We were very surprised by the results, and so I will also give the link to that paper, and if anyone is interested in that, you can also see the implementation over there.
Perhaps naive or question, maybe you addressed this already, but for you guys who are working on causality, um, I'm you earlier mentioned this notion that when something increases, the variability in something else can change or increase, as opposed to A increases, B increases, which is a direct regression. There's a different kind of causality, which is when A changes, it causes a change in something other than the magnitude, its variability or something, which is, of course, very interesting. I'm curious about something that in my brain I'm naively calling conditional causality,
Okay.
which is that a causal relationship only exists under certain conditions, meaning some other variable has to be above a certain threshold uh, or so on. Yeah.
Yeah,
Um,
yeah,
there's a sort of interesting connection there to machine learning in the sense that when you use a rectified linear unit, the variables that decide whether the rectified linear unit is activated or not can be thought of as variables that turn on or off the response coming out of that rectified linear unit, right? So I'm curious to what extent this analysis has progressed, because one of the big differences between conceptual watershed models and machine learning based watershed models is that in conceptual watershed models, you tend to have a lot of these switching mechanisms. You know, something happens only if something else has exceeded a particular threshold. Yeah. Anyway, somewhat
yeah,
naive question, but I'm just curious to hear what your thoughts
yeah.
on that and how that's approached in the causality literature. Yeah.
Yeah, I'm hoping that I've understood your question, and there are two thoughts I have on that. The first one is actually something I would just quickly share that a quick experiment that I did myself because I was very curious.
Oh, just to mention while you're thinking about while you're bringing that up, Alison, that in some sense this might relate also to the notion of synergy. Um, yeah, yeah,
Yeah,
okay.
that was my second point actually,
Yeah.
on synergy. So here, what I did was that I was curious about something like, okay, we don't know how many variables we can condition on to get the best causality. So what if we created a toy model where we have 5 variables, but we only observed 3 of them? And so this was the basis for the experiment that I did here. And of course, I was thinking about this because the students kept asking, do we need to add this and do we need to add that? I said, okay, let's just do this experiment. And so here, let me see. Okay, I'll just try to explain it here. So I have these 3 variables. Of course, you have a mutual causality here, and then you have a univariate causality here, and then another one from here, x3 to x1, different magnitudes as well. And then you have these confounders that we don't include in the causal estimation or in information flow estimation. So the information flow estimation is only based on the 3 of them. And the question that we ask is, you know, how do the causal structures change? I don't provide the extra bit of information here, but I sort of went bananas on this and spent a whole month just really digging through every single parameter in the information flow derivation. And then I realized that, so essentially, as in the information flow, one of the things that it seems to happen is that because we quantify the background noise, if I should put it that way, all that background noise can be frozen as well. And then all you are left with is what you have in the bucket of variables that you are observing. And so, and this is also why sort of variability, measuring variability helps in that case. And so we realized that even when you have these confounders that are not included in the observation, we could still get a very faithful structure, causal structure of it. So here, T3 to 2 over here, we can see that even when we increase the confounder strength, it doesn't necessarily change the causal structure. I guess the lesson that I learned from this was that, of course, the values would always change. The magnitude of causality would change, but to some extent, if our statistical, if we have enough data samples, of course, then we could obtain some sort of statistical significance that reflects the structure, not necessarily the magnitude of causality, but the structure of causality. So does A cause B? We can still answer that question. Does A cause B or does B cause C or something? We can still answer that question. As to whether the magnitudes are different, that would change. And I didn't just try this with the information flow. I also tried this with Granger causality. I did this with Granger causality as well, using a framework that was developed by Daniel Marinazzo. Marinazzo published in PRL, where he introduces something called the kernel Granger causality, which is sort of a nonlinear estimation of Granger causality, and he also has it in the, and then so he presents that with a linear form, and that has been tested quite well in literature. And we saw the same thing from that one as well, that even when you compare these two, sort of the nonlinear estimation with the linear estimation, the difference actually, if there is causality, the difference lies in the magnitude and not necessarily in the structure of causality. That is, if we have obtained a faithful causality. The next point that I was about to mention is what you already hinted at, which is that when we later on developed the nonlinear form of the Liang-Kleeman information flow, one of the terms that we ended up bringing was the synergy. So we introduced the synergistic term. We haven't quantified redundancy as in the case of Allison, but in our case we have unique and then synergistic quantity. And again, the property still remains, and this was actually what Liang found in his 2018 paper published in Chaos, that he says that whether you operate in the linear system or a nonlinear system, the property of causality would always or should always be the same. Because if causality is a physical notion, then regardless of whether you operate, with this or that, you would always have the causal structure maintained. And what would actually change is the value. So I played around with the synergy term as well, trying to see if this would really impact it. And I realized that it didn't make, at least in for the information flow, there are the limitations that I'm still yet to explore. But we didn't see a significant difference, which is that if there is indeed causality, then this will be maintained regardless of whether you're in a deterministic system or stochastic system or something like that. And that was very interesting to see, but then also I'm aware that we have a lot of assumptions that we've made in the model, in the formalism, and so these are just good guesses, I guess, or I have just been very lucky to to design experiments that fit what I want or my biases, and perhaps maybe the best way would be to get someone to challenge those biases that I have and move beyond that. Um, so yeah, that's sort of what I've explored so far.
Yeah, that makes sense. The thing I'm trying to understand is this, and maybe my conceptual approach is wrong, but I think of I think of there being something I might call a smooth nonlinearity, right? Whereas a minor deviation from a linear system, or it can be fairly major. And then there's something else I might call an abrupt nonlinearity, which is where I flip a switch, something changes, and the entire structure of my directed graph is different. Okay. So you could say that that's part of a bigger structure, which is conditional, and at some points I only observe enough information to identify this part of the graph, and I would have to have a different kind of information to identify another part of the graph, and so on, an extreme event, for example, um, and so on. But so that's sort of what I'm curious about. It's sort of like intuitively as a human, I walk around using the word causal all the time, but I could say, well, X causes Y only if A is greater than B. And if A is less than B, then it has no, it has no effect or
I
something
agree.
like that.
I
That's the
agree.
kind of causality I was asking you about.
Yeah, I agree. I agree. And yeah, actually, this was sort of what we were testing in this in this study.
Hmm.
Um, and initially, I may be wrong. I think I was wrong. But maybe some of you also tested this idea. But I initially I thought that if Pearl is right and causality would always include or would always have correlations as some kind of foundation. So that's the first level. Then we could, in a sense, look at the correlation of the predictor and target, or the driver and the effect to and the response variable, and using the correlation between them. So my first thought was that, and this was what we tried, but it failed, that if their correlation is strong, then it then potentially the causal structure would not change if we introduce more variables into it. Um, and then if the correlation was was close to zero, not insignificant, but close to zero, which meant that they didn't have a very sort of a linear relationship between them. So the dependency is very low. Then potentially, if you introduce extra variables, it would explain more, and so the structure would
So,
change.
so in that context, sorry, let me modify my question a little bit. Um, do you distinguish between causal variables and mediating variables?
Yes,
Okay,
yes,
and
yes.
how? In other words, there may be something which is causing it, but the strength of the causality depends on something else. It's not causal by itself.
Yeah,
Yeah.
yeah, yeah, and that's that's again, this is one of the things that we tested here. So we have
Okay.
the
Sorry, I missed
mediator
that part.
dominance index over here, and we realized that this was very. Oh, sorry, this one over here. Uh, uh, I should have also shown you this, but I also tried this idea where I created a toy model and I had the mediating variables, like what I have down here for this particular one, where I had the mediating variable. So, for instance, in this case, x x2, sorry, is it yeah, x3, x3. Oh yeah, that was a different, yeah, it was a different one. So in the earlier one, this particular x3 to x1 was not there. It was not there. So that was a different one. X3 to x1 was not there, but we only had from x3, x1 to x2.
But
And then I tested the Liang-Kleeman. And what I did was that I used that idea to develop these indices so that we could tell if we could identify whether a particular variable was a mediator or it was a causal variable. Initially, I was a bit ambitious. I wanted to see if I could tell a mediator from a confounder, but I realized that was almost impossible. But then, so you
but
would see, sorry, yeah, go
if you could
ahead.
go back to your picture,
Yeah,
right?
yeah,
The graph implies that x3 affects x2,
yeah.
and x3 affects x1. When I think of mediation, I would think of um, x3 affects the relationship between x2 and x1. In other words, the arrow would be
Ah,
pointing to the other arrow as opposed to
yes,
pointing to the
yes,
variable itself.
yes, yes. And this
It's
is
much
what,
like in LSTMs you have gating variables, and the gating variables, the strength of the gating is mediated
yeah.
by other variables, right?
I
Yeah.
definitely, I do have a paper that explored that as well. So what it did was that it's converted, it developed something called subsystems, so that it's not uh, the causality is not impacting a particular variable, but it's actually impacting a relationship between A and B.
Okay.
Yeah,
Okay.
and this is also an implementation of the Liang as well, and it did that, and that is something that it's on my next to-do list to further explore as well, and to see how that will be different from what we are doing now. But yeah, I haven't explored it, but I did try it. I had one a few analysis where I compared just conditioning, like the ones that we are doing right now, so x3 to x2, and then the other form where I create a subsystem from x1 to x2, becomes a subsystem, and I see how x3 impacts. And the reason why I do that is because I think of a situation like heat waves. So for heat waves, or for droughts, one of the things that we understand is that at the large scale, SSTs provide some sort of causal information for what happens. They establish a blocking system in the atmosphere, and that would result in extremes, and they'll change the Rossby waves here and there. And so, if you are looking at, so for soil moisture to become a deficit such that it would amplify the overlaying temperature, or there will be a deficit in precipitation, then the large scale effect has to create this preliminary condition or precondition for that to happen. So the way I tested it was to see um, if I could create a system like one subsystem as soil moisture and the atmosphere, or soil moisture and temperature, and then I have another one as SST. And only when SST came to a certain condition of causality um, to that subsystem, would we have soil moisture being able to actually cause a heat wave or something like that. So this is actually what I am one thing that I'm testing as well to see, and I look forward to see how the difficulty with that is that you would always have to wrestle with timescales. So for instance, SST is a very slow varying variable, and then you have soil moisture and say precipitation or temperature being a much faster one. And so you'd have to find a way to reconcile their different timescales of operation, which is what I've been thinking about and how to harmonize that. Maybe use some kind of empirical mode decomposition or something like that. But yeah, it's something that I've been thinking about. You are muted, Hojan. Yeah.
Yeah, thanks for that. I just wanted to mention, if you think of it from the point of view of a long LSTM, you can have the time scale of the state variable be one thing, and you can have the time scale of the gating mechanism be something completely
Yeah,
different in principle.
yeah. That's true. That's true.
All right. Sorry, we're at 11:30.
Yeah.
Sorry, I took a lot of time. Anybody else have questions for Daniel?
I guess I'll just say one more point. So you mentioned, so I can see how you thought this from Pearl's like ladder of causality, but I don't think that Pearl necessarily thinks that you need correlation in order to have causation. It's just kind of a common assumption within the
Yeah.
causality
Yeah.
literature. It's called
Yeah.
like faithfulness,
Yeah.
where you kind of
Yeah.
require that. But it's really an assumption. It's not necessarily
Yeah.
true.
Yeah. 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 You're right. That's true. Yeah, that's true. Because yeah, there are times that uh, we've looked at the causality structure, and we saw that there was causality from A to B, but the correlation was was sort of insignificant. So that is definitely a point. Yeah, I don't know if that would change the sort of the mantra of correlation. Causation implies correlation, but correlation does not imply causation. I don't know if that would change, but if yeah, I guess that is something for us to keep exploring and define later.
Yeah, there are definitely some examples where you can create causation but no correlations.
Yeah, yeah, I agree with you more now than before after doing a lot of tests on this idea, because I was so convinced at a point that this was true, and then after my months of tests, I realized it actually wasn't true, and so yeah, sometimes you would not
Big
see
part of the
correlation.
problem, I think, is also in the definition of correlation, because typically we mean linear correlation.
That's
Um,
true. Yeah,
and so a lot of these things are plagued by definitional
yeah,
problems.
yeah. That's true. That's very true. Even for causality, right? That's
Yeah.
defined differently based on which reference that you're using. So yeah. Um,
Luis, you had a question?
Yes, I'm going to kind of change the topic because it's kind of a question that I always have been having this question trying to ask, but nobody's kind of answering that. Related with the idea of causality is that each time that I'm watching this kind of a graph, basically you are, especially when you're working with time, and saying, okay, you have this kind of connection with one time step or two time step in the past, and at the same time you have a connection with another variable that's one lag in the time, something like that. Basically, for me, this is kind of the way how I'm understanding that is basically this is kind of a find a different representation of the state. Or we can, so in some way, when I watching this kind of figure, for me, it's kind of basically you are kind of discovering a partial differential equation that is there. So if you have kind of connection with two time step in the past or three, basically, okay, maybe we can kind of transform that in kind of equation. Okay, this is a PDE, so this is the second derivative or the first derivative. Because for me, the kind of this strength that you have with, especially when you was talking about that is the kind of closest time step in the past that is important, or are the two, three of them? Basically, if you have two or three, basically you are working with the second derivative or the third derivative. Basically, but basically this is what you need. And this is basically is the structure that is there, that is a equation or a relationship that is there. So I don't know if somebody have been working with this idea to transform this graph in some equation. Do you know if somebody's doing something like that?
Just one quick comment on that. I haven't seen any work on that, but it's very interesting. So there's a difference between like correlation and partial correlation, right? So if you condition on time t minus one and you still have correlation with time t minus two, then hmm, then I don't think it's representable by a differential equation anymore.
But when you are working with a second derivative, really you need two time step in the past to represent a second derivative. So, or at least when you are doing this kind of representation, time
Yeah.
difference, you can have this kind of
Yes.
two time step, three time step in the past, something like that.
Uh, but so I'm thinking, hmm,
Maybe I completely wrong. This is kind of my
yeah.
my
No,
understanding
you are
about this kind
right.
of graph.
Yeah, it's an interesting connection, but I just kn like it feels like the differential equations are representing state variables and it should be Markov. But I do see your point with the computer representation of higher order Taylor expansions of the state. Yeah. Yeah, it's an interesting question.
If you don't, uh, let's say you've got position, velocity, and acceleration, and you measure only position and velocity, then acceleration becomes like that unobserved variable that Daniel was referring to, where the position depends both on velocity and acceleration, but you don't have an observation of acceleration. So you end up having to use two values of velocity in order to get the rate of change of velocity in order to infer. So to me, that's the sort of physicist's approach to lagged causality, right? The assumption in physics is that only what's happening in this moment can affect what happens in the next moment if it's a Markov process. And if you can show that it also depends on what happened in the previous time, it just means I haven't kept track of some state of the system that I need to keep track of. Whether that's the only way to look at it or not is a good question. But that's the way we've all been brainwashed to think about it. So
Oh,
at
yeah,
least,
and Lewis, you actually don't need previous time steps, right? Because as long as you tend, delta t or h or however you represent that to zero, then you have zero error, right? So we represent these derivatives with more and more time steps, or like higher order Taylor approximations, because we want to keep our time stepping kind of practical, right? But uh, if we somehow had like a analog computer or whatever that could evaluate these things continuously, we wouldn't need extra time steps to represent differential equations.
You're saying the extra time steps are just
It's just for decreasing your numerical errors. That's all.
well,
It's just a practical
no,
way of doing
no,
it.
no. If I just give you position only,
Yeah.
and I ask you to predict the behavior of the particle into the future, the causal behavior of the particle into the future,
Yeah.
if I don't also give you its velocity and its acceleration at that point in time, I can't do it. So I have to get that information from somewhere.
Uh,
That's the point. That's the point about physics I was trying to make. And if I don't have those
yeah, you
derivatives,
need
then
your derivative, of
yeah,
course, but you don't need any extra time steps.
no,
So,
correct.
yeah.
But if you don't have those derivatives, they're like the missing variables in Daniel's thing, things that you didn't observe. Then you
Right.
end up using previous time steps as surrogates to help you infer something about what those missing variables might be. They become informationally useful.
Mhm.
And for some reason, I don't know if you guys, any of you know why, we seem to be content with just velocity and acceleration in order to make predictions. Why is it that we don't need, is anybody actually aware of? I mean, this is related to Newton's laws, I guess, but for some reason you don't need the rate of change um, in order to do accurate predictions.
Well, in Newtonian physics, we can assume that to be a constant, right?
Because force is equal to ma basically says as long as you
Yeah,
have the
yeah,
second rate of change, then
yeah,
you're done, right?
exactly.
Does anybody know why theoretically that or conceptually that has to be true? Other than saying Newton said so and therefore it must be true.
Well, I guess because we have a frame of reference, right? It's we are estimating processes and states on Earth. Um, so of course, if you were to expand that domain to the Milky Way, then you would have to then that assumption breaks down.
So gravity is the second derivative, so you'd have to have the rate of change of gravity, so you'd have to
Yes,
have
exactly.
something
Yeah.
on. Okay.
So that's sort of the way I think about it. But even with what we have, we are also still bound by Heisenberg's uncertainty principle. Um, and so it, these are sort of the things that I sometimes I spend the whole day thinking about. uh, but yeah, I think, but I do see the appeal in what Louis said. It's also something that I have. It brings me back to what we discussed the last time, talking about the manifolds, right? Uh, and so this sort of makes sense to me. If we need to correct for the errors, then yeah. And I've also thought about whether should we be looking at accumulation of time or we look at lags, um, which is something that I'm currently have a student working on. She comparing whether you look at lags or you look at accumulation because I mean the assumption we are making is that if it's lag two that is the strongest, you know we can't just skip lag one. There has to be some sort of integration of the process, but it's it's
I did hear a talk by Casti at I think it was at the New Mexico Institute. I could be wrong, where he did an informational analysis using Venn diagrams, and he suggested that you could have causal information which bypasses the current time step, which I thought was a little bit okay, maybe mathematically demonstrable, but conceptually kind of blows your mind. It's like saying that something that happened uh, a week ago suddenly affects what's happening now without it having passed through the intervening time, like spooky action at a distance or something like that. But I'm sorry,
Well, of course, we have that for non-state variables, right? Like streamflow acts like that.
this-
It has
yeah,
like causal links that are past
yeah.
3 days with itself.
But isn't that because of missing
Right. Yeah.
variables? Yeah.
There's
Okay.
some intermediate variables that are state variables, but
Okay.
yeah.
So it appears to be causal, but it's
Right.
yeah. Okay. All right, guys, I got to go. But that was a very interesting conversation. Thank you, Daniel. It was
Thank you
really
too.
interesting to hear your work.
Yeah.
I was not aware that you were so deep into this stuff. So that added a very
Yeah.
nice. I mean,
Please.
Joe and others have been pushing the we need to pay more attention to causality thing. So it's nice to see that there's actually a fairly sizable group doing that. And it would be interesting at some point to come back and talk more about, um, its relevance to machine learning. You sort of started the conversation. I think the way you put it in was as regularizing principles
Mm.
on machine learning. And I need to sort of sleep on, okay, is that the only and the best way to do it, or is there something
Yeah.
deeper or more fundamental? Yeah.
Yeah. I would really
Writing a
appreciate
proposal about that
afterthoughts.
now. Yeah.
Yeah.
There you go.
I'd appreciate afterthoughts. So please feel free to send me an email if if something comes up in your mind concerning this. Thank you so
Sure.
much. Okay.
All right. See you guys in the 3 weeks.
Bye.
Okay, thank
Bye.
you. Bye.